Okay, so last week we talked about how to determine what the formula of an ionic compound is based off of the charges of the ions and how to find those charges. Um, and today we're going to talk about how we would actually name those, what we would call them when we see the formula. All right, so just real quick, give you guys a refresher, the difference between ionic and covalent compounds. In covalent bonds, the electrons are shared between the two atoms. So if you see here in this covalent bond, these electrons are being shared. They're in the orbitals of both of these atoms. Same thing over here. So the hydrogen and the oxygen are both claiming these electrons. And covalent bonds are typically from a nonmetal to another nonmetal. So you can see oxygen and hydrogen, they're both nonmetals. So that's how you can kind of assume that this is a covalent bond. All right, ionic bonds are the opposite. They're usually from a metal to a nonmetal. So instead of being two nonmetals, one of them is a metal, your sodium, the other one's nonmetal. And instead of them sharing the electron, one of these is giving away an electron and just it doesn't have any claim on it anymore, and the other one is taking it. So you can see this electron here was taken from this outer shell of the sodium. It's no longer there. It's now with the chlorine. The sodium no longer has any attachment or claim to it. All right, so that's how you can tell the difference between them. When we are naming them, there's two main types of ionic compounds. There's binary ionic compounds, and there's polyatomic ionic compounds. We've talked about both briefly before, so you should be able to tell the difference. And the ways that you name them are slightly different as well. So when we're talking about binary ionic compounds, the first thing you want to figure out is whether or not your metal is a metal that has more than one possible charge to it. So if your metal is one of the first two metals in the first two columns, either alkali metals or alkaline earth metals, or if it's one of the ones over on the right side of the periodic table past the transition metals, where it's in the row like aluminum or gallium or tin in carbon's row, where you can tell its charge based off of that, then you don't have to worry about putting the charge in your name of the formula. So if it's one of those metals where it only has one possible charge, it will be the name of the cation, so the name of whatever metal is in your bond, and then the name of the anion, which would be whatever nonmetal it's bonding to. But at the end of the anion, you take off the end of that chemical and you replace the end with ide, IDE. So I'll show you an example of that in a couple seconds. The other form that this can take is if it's a transition metal, which are those ones in the middle between the first two columns and the right side of the periodic table, that whole middle section. Those ones have multiple possible charges. They can have different numbers of valence electrons and different charges. So when you are writing out what the formula is or the name of it, you've got to put the charge of what that cation ends up being in parentheses as a Roman numeral. So it's the same thing, the name of the metal, then its charge in parentheses as Roman numerals, and then the name of whatever nonmetal it's bonding to with the end of it replaced with IDE. All right, so some examples of that are going to look like this. So if we have this, and then you go and open your periodic table, you can see that K is potassium. Okay, I actually brought up the periodic table here. So we can see that K, if we hover over it here, the name of that is potassium. And Br over here is bromine. So if we're looking at naming this compound, well, we know that K is in this first column, so it's not a transition metal. So it's only ever going to have the one charge. And if it's in the first column, that charge is going to be positive 1. So we don't have to worry about putting the Roman numerals in there. So the name of this would just be potassium bromide. So we took bromine, took off that last little section of it, and replaced it with IDE. So it's potassium bromide. All right, our second one, we've got sodium, Na, over here. And then we've got oxygen over here on the right. That's the O in our formula. All right, so again, this is a metal that's in these first two columns over here. So we know what its charge is going to be. We don't have to worry about it having multiple possible charges. So we don't have to worry about having the Roman numerals in our formula name. We would just have sodium, and then instead of oxygen, it's oxide. We take off the last section of it and we replace it with IDE. All right, and then this third one, we've got iron, and so Fe, you can see is iron, and Cl is chlorine. So this would be iron chloride, but because Fe is in this middle section, it's a transition metal. So we're gonna have to give it a Roman numeral to show what its charge would be. So this is where we could go back to what we were doing last week with determining the charges. Say we know chlorine over here, it's in this 7th column, or the 2nd column from the left. So we know it's going to have 7 valence electrons. So when it forms an ion, it will get 1 more electron to fill up the outer shell and become -1 as its charge. So each chlorine has a charge of -1, and in our formula here, we've got 3 chlorines. So that's a total of -3, which means for this to be neutral, the charge needs to be +3 on our iron, our cation. So that should be stuff you're familiar with from last week. So if we were going to name this, we would say iron, and then we know its charge is +3. So in parentheses after iron, we're going to put Roman numeral 3, chloride. And the name, we take chlorine and replace the end of it with IDE. All right, so those are some examples. We can also do this going the other way. If they're giving us the name, we can use that to find the formula. So this is another time where you're going to have to know how to find the charge of something, or else you're going to be really stuck knowing how many of each thing you need. So for calcium oxide, we can look over here and find calcium. Look over here, oxide means oxygen. So we know it's going to be some number of calciums and oxygens bonded together. And to know what number of each we're going to need, that's where we've got to find the charges. So just like we did last week, if calcium is in this 2nd column, that means it has 2 valence electrons, which means when it turns into an ion, it's going to want to get rid of those 2 and end up with a charge of +2. Oxygen's in this column here, the 3rd from the right, which means it has 6 valence electrons. So it wants to gain 2 electrons to get up to 8, and that would give it a charge of -2. So if we have calciums with +2 and oxygens with -2 each, we just need 1 of each and they'll cancel each other out perfectly. So here, our calcium oxide ends up looking like CaO as a formula with just 1 of each of these atoms. All right, this next one, lead 4 fluoride. So this 4 here is telling us the charge of the lead. So we don't have to worry about finding out what the charge of lead is going to be because it's telling us what it is in the formula. So if we go find lead, it's right here. It's Pb on the periodic table. So we know we're going to have Pb as one of our elements here, and fluoride means that our anion, the nonmetal, is going to be fluorine. All right, fluorine's over here in the 7th column, or the 2nd column from the right. So it has 7 valence electrons. That means in order to get to a full outer shell, it needs to get 1 more electron, which gives it a charge of -1. All right, so if we're trying to make a balanced compound, and we know that the lead has a charge of +4, we would need 4 fluorines to balance that out if they're each worth -1. Right, so a lot of this is the exact same stuff you were doing last week with balancing the charges and all that. It's just being able to read the formula in words and kind of translate that to an actual chemical formula, and vice versa. All right, and this last one, copper 1 nitride. So we'll find copper on the periodic table so that we can know its symbol. It's right here. Its symbol is Cu. All right, we know it's going to have a charge of +1 because that's the Roman numerals that we've been given. And then nitride tells us that our anion is going to be nitrogen. So nitrogen, we can tell by the column that it's in that as an ion, it will have a charge of -3. So if the nitrogen is -3 and each copper is +1, we need 3 coppers to cancel out the 1 nitrogen. All right, it's all the same stuff we were doing last week. So this is what your formula for that would look like. Okay, so that's binary, where you've got basically just 2 different elements. The other type that you got to worry about is polyatomic ionic compounds. All right, and so these are compounds. Oh, let me hide this periodic table real quick for you. So the polyatomic ionic compounds are ones that have polyatomic ions in them. Surprise, surprise. And they're named using the same kind of procedure where we put the cation first and then the anion second. The only difference is we don't replace the end of the polyatomics with IDE. We just call them by their names. So for example, KNO3, where we've got the cation of potassium and the anion is this polyatomic nitrate, we would just call it potassium nitrate. So for these, you're just sticking 2 words together. You do still have to worry about putting the Roman numerals in there if we're using a transition metal, but that's the same as the other one, so it's nothing new. All right, so let's skip forward. The next slide. All right, so same kind of deal. It's giving you the name, and it wants you to find the formula. So here for barium nitrate, well, let's see if we can. Okay, so we've got this list of common polyatomic ions that you guys had last week, and we've got the periodic table. So I'll be flipping back and forth between these as we do these problems. So if we're trying to find the formula for these, we've got barium nitrate as our first one. So barium, if we look for it, we find it down here in this second column. So again, it's not one that we need to worry about having multiple different charges. Excuse me. So we won't need the Roman numerals in our answer because it's in this first 2 columns. And because it's in the second column, we know its charge is going to be +2. All right, and then nitrate, if we go and look on our list of common polyatomics over here, we can look and find nitrate right here. And it's going to be NO3 minus. That's what nitrate is. So if we know barium is +2 and nitrate is -1 each, we're going to need 2 nitrates to cancel out the +2 from the bariums. So just like last week, you're going to write that as Ba and then your NO3 in parentheses with how many of them you need on the outside. All right, pretty straightforward. For the ammonium iodide, so this one's a little tricky because your polyatomic is actually your cation on this one, right? Usually the polyatomics are going to be the negative charged ones, so they'll be the anions. But in this case, you've got ammonium as your cation. So if we look and we find here ammonium, that's NH4 plus. So we know it has a charge of +1. And then iodide, if you remember replacing the IDE on the end, means that this is going to be a single element. So if we go find iodine on the periodic table over here, we can look at the column it's in and determine that it would have a charge of -1. So if we've got a +1 from the ammonium and a -1 from the iodine, they cancel each other out. You just need 1 of each. So it would just be NH4I. Simple enough. All right, this one here, it's iron. So we know that's going to be on our periodic table Fe. So that'll be the symbol we're looking at. And it's iron 3. It gives us in the name. So we know its charge is going to be positive 3. All right. Then we've got to go find hydroxide for our polyatomic. So if we look, find hydroxide here, and we see that the formula for that is OH minus. So hydroxide has a charge of -1. Our iron 3 has a charge of positive 3. So we're going to need 3 hydroxides to cancel that out. So we'd put our iron, Fe, hydroxide in parentheses with how many of it you need outside. So FeOH3 would be the formula for this. All right, and you can do this going the opposite way as well. You can take the formula and write names for it. So here we've got K2. So K, if we look on the periodic table, is potassium. It's a first column metal, so we don't have to worry about putting the parentheses in there with the Roman numerals because it will always have a charge of positive 1. And then we go find over here CrO4. If we look over here, we'll find chromate is the name of that molecule, that ion. So if all we're doing here is putting those two names together, we would say potassium for the K, chromate for the CrO4, and the name of it is just potassium chromate. Easy peasy. Okay, the second one, if we look and find Mn on the periodic table, it's right here. The name of that is manganese, and this is a transition metal in this middle chunk, so it is going to need the Roman numerals. So we've got to find out what the charge of it will be so we know what the Roman numerals end up being. So in order to figure that out, we look at our anion, NO2, and we see if we can find that anywhere here. And if we look, we find NO2 right there, and it's called nitrite, and it has a charge of -1. So if nitrite has a charge of -1, and this is saying we have 2 of them, because that's what's on the outside of the parentheses, that's a total of -2 from the nitrites, which means that the manganese has to be +2 to cancel it out. So we would say manganese 2, Roman numerals in our parentheses, to show that it's a +2 charge, and then nitrite. Okay. So the last page of this slide that I'll be putting up on Canvas has a link to a periodic table y'all can use right here, and then it has let me turn this off. It has a list of some of the common polyatomics with their charges that you can use here when you're naming things. All right, so you guys should be working on this homework, and that'll be all you're doing today.